we have a little ceremony because NCTS as a program to try to stimulate the research in the community, especially for young, promising brilliant physicists in the community. So we have an award called the NCTS Young Theorist Award, and it's annual every year as a selection. And this year, after a very severe competition, we have selected one person, which is basically we can get. So the competition is open to all fields, including people from condensed matter, AMO, and soft biology. And eventually, he got the. So we are presenting this award, and then this talk is part of the deal to get the award.
Shake hands.
Shake hands. Okay. Thank you.
Okay, so our next talker is Professor Ting Huang. I talk about UER polytopes. That's what I mean.
Thank you very much, and thank you, Chong-Sen, for the ceremony. Yeah, I mean, actually, this talk is probably very suitable in this context. I mean, NCTS has really been very supportive of our young researchers, and in fact, giving support and giving opportunities. And in fact, like for example, yesterday there was the two students who gave a talk. My students who gave a talk here, Zizong Li and Sun Qing Zhang. And for today, my talk will be based on a collaboration with also students and young generations of physicists in Taiwan. So Ting Huang, which was a previous student of mine, and Su-Hen Xiao is also a previous student of NTU, and we're currently a postdoc at the Institute, and collaboration with Nimara Kami. So really, there's many talented young researchers in Taiwan, and yeah, we're very thankful for NCTS for their support. So this talk is about carving out the space of consistent quantum field theories. And basically the idea is that for the past couple of years, there's been really a progress of geometrizing what we usually consider as the fundamental physical principles. For example, the notion of unitarity, the notion of locality, and various symmetries of the theory. All these properties we usually take as the fundamental properties of physical systems. And in the past few years, we've been able to geometrize these notions, and instead of stating it as a fundamental property, as emergent properties from certain geometric properties. And this geometrization was succeeded through the lens of particular physical observables. So for example, planar n=4 super Yang mills has been realized as a particular, the scattering amplitude of n=4 super Yang mill has been realized as a polytope in crystal space. You might say that this is a very special theory, this is planar n=4, but recently people have realized that actually even just ordinary tree level phi cube theory and quantum field theory textbook, it can also be realized as a polytope in the Mandel-Span space. And when I say that it's a polytope, what do I mean? I mean that the polytope is there's a polytope in the space, and of course, once you have this space, then you have to define an object on this space, and basically you have to define a differential form, which usually when you have a space, you want a differential form in order to integrate over the space. And the differential form is determined by the particular singularities that it has on the boundaries of these polytopes. And that answer is just directly is the amplitude. Okay, so we know that amplitudes has to satisfy all of these properties, and therefore in this picture, all of these properties are just reflected in a particular structure of this polytope in the various spaces. So of course, still, this is just n=4 super Yang mills, and this is just tree level. And of course, the grand hope is that all of these properties can literally we just replace all these properties with just a geometric statement. So the question is there any sense in which this kind of picture can be universal? And we would like to make this question more precise. What can we geometrize the constraint of unitarity and symmetries for general quantum field theory? So when we talk about general quantum field theory, what do we mean? We mean that we consider a space of all theories. And the space is basically you have fixed points, which are the CFTs, and between the fixed points you have RG flows. So this will be the picture of the space of general quantum field theories. On the fixed points, your description is a CFT. On the RG flow, essentially the description is you have an effective field theory. So the question you might want to ask is, first of all, through which observable is this geometry realized? And furthermore, what are the content you want to constrain? So of course, on the CFT side, you know that the observable is essentially, you don't have S matrix. So the observable is a 4-point, for example, you have the 4-point correlation function. And the thing that you might want to constrain is, for example, the conformal dimension of your primary operators and the 3-point coupling. On the effective field theory, along this RG flow, where you basically have an effective field theory, and once you have an effective field theory, you can define your S matrix. So the observable you want to target will be your S matrix. And then what is the content you want to constrain? The content will be these coefficients for the higher dimension operators, or the relevant operators. So the task of so basically the story of my talk is I want to say that the description for the S matrix and the 4-point correlation function, there is a polytope in general sitting there. And I would like to tell you what this polytope is. So first of all, let me begin with the effective field theory. So let's just take things simple and let's just consider an effective field theory. And in effective field theory, basically, what we mean by effective field theory, we know that there's some UV fixed point or some UV theory that completes your theory. And then you're just looking at the low energy. And therefore, in the low energy, all these UV information are encoded in your higher dimension of the coefficients of these higher dimension operators. And these coefficients, in turn, appear in the 4-point. For example, the 4-point S matrix, in a way in which, if you look at the 4-point S matrix in terms of Mandelstam variable, then generically it will have a polynomial expansion. These coefficients in your polynomial expansion could encode the information of the coefficients for a higher dimension operator. So therefore, for example, if you have some theory with partial phi to the 4, a higher dimension operator, this A will appear in your 4-point S matrix as a coefficient sitting in front of these polynomials. Okay. So basically, we want to talk about for effective field theories, you can talk about these coefficients in your polynomial expansion. Now, naively, you would say that without knowing what the UV completion is, there's really nothing you can say about these coefficients. And this is the naive point of view.
So you include higher derivative term.
Right, we're talking about a higher derivative.
But there's the unitarity may not be obvious.
So that's what okay, so let's talk about what does unitarity mean here. So for example, the statement is precisely that the unitarity actually fixes the sign of these coefficients. And it's a very simple one-line argument. For example, if I look at the 4 limit, which would be that when t equals 0, then I can pick out some coefficients. So for example, if t equals 0, then I'm picking out the gi0 piece. So this gi0 can be written as a contour integral of this S matrix element, where the contour is encircling the origin. Now you can deform this contour into this bigger contour, but you cannot deform it all the way to infinity because you know precisely because there's some UV physics that there's going to be poles or branch cut along the real axis. And therefore, this coefficient is related to the imaginary part of your 4 limit because this integral is going below and above the real axis. And the important, so you say the unitarity is not obvious, but no, we know it's obvious because we know that any time when you have an imaginary part of your S matrix, unitarity tells you the optical theorem tells you that it has to be related to the cross-section. And you know that the cross-section is positive. I mean, since a physical observer is positive. And therefore, this in turn tells you that unitarity is telling you that this coefficient here has to be positive. So there's already a constraint but this constraint was already known around 15 years ago, actually. Yes, I think, yeah, but this is already known 15 years ago.
10 years.
10 years? Okay. So, of course, one of the important statements here was that we know that there was a bound on the behavior of the 4 limit amplitude at infinity, and therefore we know that this contribution will not contribute. But in general, there is actually also bound on the amplitude on the 4-point S matrix at infinity, just from causality alone. So causality bounds that this amplitude cannot behave greater than s squared at fixed t. So once I tell you this, that means that I can actually do a similar analysis as before, but this time not at t equals 0. Now, of course, if it's not t equals 0, then I don't have the optical theorem anymore. So what would I have? So the majority of the talk will be what is that object that I have, the constraint from unitarity. But anyway, as long as I have some kind of bound at infinity, that means I can do the same discussion again, just with some particular subtraction. And what that implies is that this 4-point function has a representation in which you basically just sum over the poles of the S and the U channel with particular numerator, which is dictated by the fact that you're computing the imaginary part, and therefore you're encircling the residue of the S and the U channel poles. So that means that there's an alternative representation for the 4-point function.
Sorry, but isn't that assumption that is bounded at infinity already some kind of assumption on unitarity? Because that.
Well, I haven't used unitarity yet, but this bound is coming from a causality. There's a causality bound.
Well, but I'm saying in some sense you're assuming the amplitude doesn't grow.
Right. So, but there's a bound. So it
right?
only grows as it can at most grows at s squared.
I understand.
And I can do subtractions. I can talk about the subtractive piece.
That's right, but I'm saying isn't that already some kind of assumption on the unitarity that you amplitude as the certain behavior, right?
Yeah. There are some assumptions, but I'm saying that there's still more constraints from unitarity. And that constraint is precisely coming from what this numerator polynomial looks like. So let's look at what that constraint is. So the constraint is basically that this numerator here has to correspond to some kind of factorized product, because this is an imaginary part of each of these discontinuities here. And therefore it has to correspond to some factorized product. And the factorized product is actually completely determined by Lorentz invariance, because the factorized product is a product of two, for example, I'm talking about scalars here. So it's basically two scalars and some arbitrary spin pieces. And this structure is completely fixed by Lorentz invariance. It can only take this form. And therefore the product of these two, the factorized product of these two is a particular polynomial. And this polynomial is basically the Geigenbauer polynomial. Which, if you're not familiar with Geigenbauer polynomial, in 4 dimensions, this polynomial just becomes a Legendre polynomial, which is precisely the partial wave expansion polynomial. So in other words, this polynomial is not a random polynomial. It must be some positive coefficient multiplied by this Geigenbauer polynomial. So the question now becomes, what constraint can we derive for the low energy effective field theory from the fact that it has a representation where it has a UV completed form that takes this form? So what does this form imply for low energy? Well, so first of all, a side note, because of the fact that I'm relating the S and the U channel together, residues together, and therefore I'm really considering a case where I'm organizing my states such that I have this SU symmetry. In that case, the natural parameters I'll use is instead of S and U, I'm going to replace S and U with this particular representation. So I have the Z polynomial. So I'm considering my low energy effective action, low energy effective field theory, the 4-point amplitude as expansion in terms of T and Z instead. Okay, so what can we say? So basically, for example, if you have a fixed mass dimension operator, that means that you have this fixed mass dimension operator. For example, let's consider a dimension 8 operator. L is 2 times the dimension. Then at low energy, it corresponds to a point in the possible dimension 8 polynomials. Okay, because at low energy, for the dimension 8 polynomials, basically there's these 3. And for a particular higher dimension operator, it corresponds to a particular coefficient for these 3 polynomials. And therefore, it's a point in this 3-dimension space. Just as an example, so for example, if we consider string theory, this is a string theory 4-point amplitude. You can expand in alpha prime. Then at the alpha prime to the 4th order, you have this particular combination. So string theory in this 3-dimension space lives at a particular point, which is 9/8, 3, and 2. So basically what I'm asking is, what are the possible allowed space within this 3-dimension? Is there a subspace in this 3-dimension space in which dictated that by unitarity and Lorentz invariance, that you have to, that any theory that is unitary and Lorentz invariance has to live in a particular subspace. So is there a way that I can frame this question? And of course, yes.
Is it the Virasoro amplitude?
This is the closed superstring amplitude. So type 2
Virasoro
amplitude.
amplitude in all days,
Yeah.
Yes.
To what extent this argument depends on the choice of fields, fundamental fields, which you studied?
So I'm looking at massless fields because obviously massless fields are the fields that you observe in the IR. So for example, so any fields that is massless.
With all possible speeds.
With the UV completion can be arbitrary massive, arbitrary spin. Right. Good, so what can we say? Well, we already know that you have a representation that takes this form, so obviously what you can do is you can just expand this in terms of polynomials and T and Z. So this is for a particular spin here. This L is a particular spin. So for each particular spin, you can just expand this polynomial out. It'll give you infinite dimension vectors in terms of the Z and T. And the point is that there's a C squared in front. Therefore, for a particular polynomial, it's essentially a C squared times a particular vector. Okay, so for example, for our 3-dimension case, for each spin, for each spin defines a particular vector in this 3-dimension space. Okay, where this 3-dimension space is for the mass dimension 8 operator. So basically, the statement is very simple. The allowed space for this higher dimension operators from unitarity and Lorentz invariant is basically spanned by it's basically a convex Hall of all of these vectors that you come from expanding this polynomial here and with the propagator here. And that's the allowed region. Now, naively, you would say that this will give you zero constraint because of the fact that you're sitting at a finite dimension space, and the expansion, the number of vectors there are infinite because for each spin you have a vector. So you're trying to span a finite dimension space with infinite vectors, and the answer is you probably will think that, well, you're not going to get any constraint, that these infinite vectors are just going to span the entire space. Well, of course, we already know that this cannot be true. It has to be only a subspace because if you look at this vector, the first component of this vector is basically evaluate your Gegenbauer polynomials at 0. So at t equals 0, which is basically looking at cosine theta, the scattering angle equal to 1. If you look up Gegenbauer polynomials in Wikipedia, you'll see this plot. And you'll see that for this plot, at x equals 1, all the polynomials are all positive. And in fact, it is precisely the 0 component positivity that was related to this GI 0 positive 10 years, this bound that was derived 10 years ago. So already you know that this coefficient cannot be negative, so you're already looking at a subspace just from the result from 10 years ago. And so now we're saying that this result, this GI 0 bigger than 0 positivity of this bound 10 years ago is really just well, basically literally just the tip of an iceberg. So there's really an infinite bound that is going upwards as you expand in T. So what does this bound look like? So let me show you. So for example, if I look at the original dimension 8 operators, which can only live in a 3-dimension space, the convex Hall of all of these vectors, I'm doing a projective invariant plot. So this is a 2-dimension projective invariant plot, which I'm basically dividing these coefficients with the third component. And this is the allowed space. This blue line is basically the allowed space where all the higher dimension operators can live. The green line is so the blue line is coming from if your UV completion is 4-dimension. The green line is coming from the UV completion in 6-dimension. The purple line is UV completion in 10 dimensions. You cannot see that. Okay, let me just. If you want to look at the dimension 10 operators, then they live in a 3-dimension space, and basically they have to live within this polytope here. So for each dimension, there exists a polytope where any consistent effective field theory must live within. And this actually tells us something interesting as well. So for example, you might imagine that perhaps you can do some fine-tuning. And so for example, for a dimension 8 operator, which lives in that 3-dimension space, you say, oh, maybe I can cook up some UV completion which has fine-tuning that tunes some of these parameters much larger than the other parameters. And this is basically telling, this analysis is basically telling there's no amount of fine-tuning that can allow you to do that, because all of these coefficients are all tied together. They all have to live within a particular boundary, particular polytope. No matter what kind of ingenious thing you can come up, you can never really fine-tune, arbitrarily fine-tune the coefficients of these higher dimension operators. So, of course, once I tell you that there's a polytope, then you want to ask, what is special about these polytopes? Because these polytopes are the geometric realization of unitarity and Lorentz events. So, if this is coming from some special symmetry and property, you want to know, is there some special property in terms of the geometry of this polytope? So, this is a plot that I plotted out, and this is actually a two-dimensional plot, and then basically, so that there was this three-dimensional vertex space that I was telling you about. I was telling you that each spin Eigenbauer polynomial defines a vector. So here I'm plotting the vectors in terms of its spin. So you see that there's a spin 5, spin 7, spin 8, spin 9, and I'm basically plotting, so each of these going back to the origin is a two-dimensional vector. And you'll see that this vector has a very special property. This vector appears to be lying on a moment curve, meaning that the value of these, the component of these is basically parameterized by 1 t squared to some dimension. And you can really show that if you take L to be large, they really are parameterized in this form. And what is special about a moment curve? Well, if you look at the points on your moment curve and you consider the convex hull of the points of a moment curve, then this is what mathematicians define as a cyclic polytope. What is a cyclic polytope? If you look at Wikipedia, this is a description of what cyclic polytope. But an important point is that it has a property that if I give you in a fixed dimension, I give you a bunch of points. You can ask, what is the polytope that maximizes the number of faces of the various dimension phases that is possible for a fixed number of points. And the maximum number is realized by the cyclic polytope. Okay? And we've been able to prove that these vectors, so there's also another definition of cyclic polytope, which is basically you take the ordered matrices constructed by these vertex vectors, and if any of the order minor, if arbitrary order minor is positive, then these vertices define a cyclic polytope. And for these Eigenbauer vectors, you can directly construct what the minors are, and you can, just by this form, you can see that it is indeed definite positive whenever the spins are ordered. So we've been able to prove that the Eigenbauer polynomial defines vectors that defines a polytope, which is cyclic. So in other words, unitarity plus Lorentz invariance in terms of a geometrized sense defines a polytope which maximizes the number of faces. So there is a geometric property associated with it. So an important property of cyclic polytopes is, first of all, you already know what the boundaries are. So basically, for various dimensions, in light of time, so basically the statement is just that you already know what the various dimension faces are for this polytope. And more importantly, under projection, the boundaries of higher dimension polytope directly lands on a lower dimension one. So for example, this is just like a triangle. The triangle is an example of a cyclic polytope, and the higher dimension, so the higher dimension faces, if you project down to, if you project through this point here, you project down, then this is still the lower dimension, this defines the lower dimension cyclic polytope. So what does the property of cyclic polytope buys us? Well, precisely this property. So imagine that you have this lower dimension, and remember, by going to higher dimension, that means that we're looking at higher dimension operators compared to the previous one, in terms of derivative. So if you have some theory that has a lower dimension, that has a particular coefficient that lives within the boundaries of the lower dimension polytope, and then you want to consider this extension of this theory to higher dimension derivatives. And you might say that, okay, then I'm going to, because then I have to consider the full four-component vector here. Then there's a new constraint that is coming back to constrain the original thing that I've derived that I verified was within the lower dimension polytope. And but precisely because of the cyclic property, no, the only thing that it constrains is actually constraining this extra component. So that once the lower dimension, your theory has a point that lives in the lower dimension polytope. When you go to higher dimension, the only thing that is constrained is this new higher dimension operator. So just to make it in a more physical statement, this is basically, and remember because I'm expanding at t when I'm going to higher dimension. So this is basically the statement of RG. And when we think about things of a renormalization group, we think about that once you define something, you can have a separation between scales, and basically once you have the separation between scales, whatever happens at the lower scale doesn't subject to constraints from the higher scales. And this is a particular realization of the fact that RG is there. Of course, this is not the usual RG. This is really RG in impact parameter space. You can ask where the string theory lies in this polytope. And this red point here is basically the type 2 closed superstring. Here you cannot even see it because it's basically living at one of the vertices here. So just to give, because this is a higher dimension polytope, so let me just show you the particular form. So this was the 2-dimension plot. Again, this is the 4-dimension polytope, the 6-dimension and 10-dimension. And you see that the string theory, the type 2 superstring, is really living at very close to the boundary of the allowed polytope. So string theory is in a sense very special. And if you want to see the corresponding 3-dimension plot, here it is. This is the shape of the polytope, just to give you the sense of, this is really a 3D shape. And so just to give you a sense that really, you see the string theory here is really sitting at very close to one of the vertex. So even
why is it only close to here? I would imagine it should be right at the edge, or right at the tip.
Well, that's a good question. Well, so right now we're still figuring, because of course this is only 3. So the polytope is really infinite dimension. You can always take a sub-dimension slice. And so the question is, does it actually approach the boundary as you go higher and higher dimension? And actually just comparing the 2 and the 3-dimension plot, you already see this, right? Because the 2-dimension plot here, it was still some distance away, but then at the 3-dimension plot, you see this is already very close to the vertex. But of course, I cannot show you the 4-dimension plot of but that's something that one can look at. But you can ask, what about the 5 different string theories? And actually, we tried to plot the 5 different string theories, but we didn't plot it because they're all the 5 different string theories are basically overlapping points. So it's they're all very close to the boundary.
When you refer to the string, it is string frequency or string amplitude?
String amplitude. Yeah. So, how much time do I have? Oh, 10 minutes. Oh, great.
So maybe
Yes.
What's the meaning of having string theory very close to?
Well, I mean, I'm going to move on from effective field theory to conformal field theories shortly. And if you remember the story about conformal field theories, there's also a similar. I mean, they've been doing similar plots, right? And when they're plotting out the space of conformal field theories, all the special theories that we have, for example, in the 3D Ising models, you notice that all of these special theories, they always live at the boundary or at the kink of these plots. But not always, but
we
generally.
why.
I think there's an understanding about why they're always close to it, but I'm not familiar with that.
In that case, I think that the bounds can be shrunken if you consider many other operators.
Right. Okay.
In this
Good.
case, in your case, this RG flow, if you go to higher dimension operator, then this bounds actually grows.
Okay. I think in that context, I can answer it in this way. So in that case, Ising models, these are very constrained theories in the sense that there are no marginal parameters that you're able to deform from these particular CFTs, right? And therefore, by considering more and more different operators on the outside, you see that it's actually an island, right? And so that there's a rigidity associated with Ising model in that particular sense. So here, I think this is also reflecting is that there's also rigidity in terms of the string theory completion. And in some sense, indeed, because perturbative string theory, it is rigid. I mean, there's not many perturbatives, there's just 5 of them. And it's very hard to deform string theory. I think in that sense, that is what this is telling me. Of course, you say that who cares about what I'm talking in terms of people who are interested in phenomenology. because I'm talking about massless scalar and higher dimension operators associated with massless scalars. You can argue that whether or not this is an interesting question. But however, in real world, the only massless fields that we have are basically just photons and gravitons. So if I really wanted to talk about effective field theories, what I really should talk about is bounding operators associated with photons and gravitons. So in other words, higher dimension operator in terms of F and R. And of course, even the standard model has a description as an effective field theory for higher dimensions of F and R, because as long as you go to energies lower than the quark mass, and the quark loop, it essentially generates these higher dimension operators in terms of F and R. So basically, this is also, standard model also has to live, or anything beyond the standard model also has to live within these polytopes, if I have a polytope for photons and gravitons. And the statement I would like to say is that yes, there is also a polytope for photons and gravitons. And it's basically a very simple, similar argument. It's basically that the 3 and 4 dimensions, the 3-point coupling between the two massless arbitrary spin particle and the arbitrary massive higher spin particle, this 3-point coupling is also unique. So remember previously I have a particular bi-Gegenbaum polynomial, and the reason that I had that polynomial is I told you that Lorentz invariance and this factorization property fixes that has to be the Gegenbaum polynomial. Here I'm also telling you that Lorentz invariance also fixes the 3-point coupling here, and therefore there's also a unique factorization polynomial. And this unique polynomial is basically the Jacobi polynomial. Okay, so the Jacobi polynomial has 2 entries, and basically the 2 entries is determined for a case when you have photons or gravitons on the outside. It's determined by the internal spin, and well, if it's photons, then this is 4, if it's gravitons, then this is 8. And so you also have a completion, using the same argument, you would have a completion of this form. And you can do exactly the same analysis that I told you about. And this is basically the shape of the polytope that you have. And of course, the first thing you want to ask is, what is the property of this polytope? And let me just, in one line, just say that it's also a cyclic polytope. So it seems that this is a consistent story, that anytime you have Lorentz invariance and factorizations, it defines an effective field theory where the effective field theory has to live within these cyclic polytopes. Okay, so I've been talking about effective field theory very long. So let's just change gear and go to CFT. So we were talking about constraints along the RG flow where all these higher dimension operator has to live within these particular polytopes. So what about at the fixed points, which you're actually sitting at the fixed, at the CFT point? So at the CFT, then we cannot talk about S matrix anymore. All we can talk about is correlation functions. So in particular, we can consider the 4-point correlation function. And here I'm just going to think about 1-dimension CFT. And the reason is because if I can prove anything for the 1D CFT, then it has to be true for higher dimension CFT, because you can always take your conformal cross ratios to a particular point, and it is essentially the higher dimension CFT 4-point function will essentially be a 1-dimension CFT. Okay, good. So let's consider the 4-point function. And the fact that the CFT is unitary, it tells you that the 4-point function can be expanded in what is called a conformal block, which corresponds to particular higher dimension particular primaries in the 3-point OPEs with some positive coefficients here. In 1 dimension, the conformal block is basically the hypergeometric function weighted by some z factors here. So since you've seen a polytope before, so we can do a similar analysis here. So let's consider the 4-point function, which is my CFT observable. And let me just expand it in terms of the cross ratio and expand around 1/2, the symmetric point. Then my 4-point function is encoded in an infinite series of coefficients with a particular order in this y with a particular coefficient. So my 4-point function is basically, again, a point in some finite dimension space if I want to truncate this y. So on the right-hand side, I can also do the expansion of the conformal block, and also has an infinite expansion. And so basically, unitarity is telling you that this 4-point function, this 4-point function vector, has to sit in the convex hall of the conformal block vector, coming from expanding, again, the conformal blocks around this symmetric point. Now, of course, we have more constraints here, and the constraint is the fact that the 4-point function has to satisfy crossing symmetry. So that just means that so this is the formula of crossing symmetry for the 4-point function. And basically what this says is that if you expand your f, again, if you expand your f in terms of the around to z equals 1/2, then these higher dimension, these coefficients have to sit within the subplane. So let's call this subplane the crossing plane x. So basically the statement, the geometry picture that we have is basically that we have a polytope which is coming from the convex hull of this C. The block vectors. And basically the 4-point function is inside this convex hull of this of these block vectors. Furthermore, we have a crossing plane. And so a consistent quantum field, consistent CFT is basically the requirement that the crossing plane has to intersect this polynomial, this polytope. So the crossing plane is determined by the conformal dimension of the external operators, because this is a crossing equation. The polytope is determined by the conformal dimension of the internal, your primary operators. So this is a constraint that is playing between the spectrum of your theory and what is on the outside. So let me just show you some plots here. So this is the plot for the 3D Ising model. So you can look at, so this is a polytope coming from a particular set of spectrum. And this is basically the crossing plane. So these 3 different polytopes is basically I'm changing the spectrum. So the shape of my polytope is basically changing. And the geometric question that you want to answer is when does these polytope actually start intersecting the crossing plane? And just to show you the extremity of Ising model, you can see that once the value of the external operators are tuned to the Ising model point, then the crossing plane is the first time the crossing plane starts intersecting. So this is another picture of showing you why the Ising model is sitting at the kink. So this picture is just showing you that if I add more and more higher dimension higher dimension primaries, the shape of the polytope basically starts changing and going higher. So the black, the green, the blue, the green, and the yellow is basically corresponds to more operators that you're adding into the spectrum, and that these operators are going to higher dimension. And the important point I just want to show you is that basically the intersection plane only intersects at the lower part, which means that the higher order parts, or the higher dimension parts of your spectrum is not really relevant for the crossing. And that is basically why these bootstrap approaches actually works, because you really don't need to care about these infinite number of higher dimension operators. Okay, since I have 1 minute, so I just go to the punchline. So basically the statement is that for these conformal blocks at the polytope that they define, these polytopes are essentially also a second polytope. So it's, again, the same polytope is appearing in conformal field theories as well. It's only the changes that, in effect, the field theory was appearing in the 4-point function, the 4-point S matrix. Here it's appearing in the 4-point correlation function. And yeah, so let me just go to directly to the conclusion. So basically, we've been able to show that there's really this general picture of geometrizing the unitarity and locality for observables in quantum field theory is really universal. It's not just in these particular n equals 4 super Yang Mills in a planar limit or some particular simple phi cube theory, but really in this along this entire picture of the space of possible quantum field theories. All of these properties of unitarity and locality can be geometrized. And what do I mean by geometrized? So the constraint imposed through factorization, where for S matrix it means in terms of the residue of the pole, or in terms of CFT it corresponds to the OP of the correlation functions, and the constraint of symmetry, which again in S matrix it corresponds to Lorentz symmetry, and for conformal field theory it corresponds to conformal symmetry. The geometric realization of these two properties is basically that the observable is bounded by a cyclic polytope. Okay, so this is basically the universal picture that we see. And this cyclic polytope is also very special, and it says it naturally leads to an RG-like picture, where the RG is now running along an impact parameter space. And this is the part that I haven't talked about, but let me just skip this part. And of course, the natural question is how do you extend this? And there's a lot of directions you can extend. For example, what is the geometric structure that lies in these conformal blocks when you're moving away from this one-dimension subspace? And of course, for general beyond standard model or just effective field theory point of view, is what does it imply for all these possible and available models, these constraints? Of course, we already say what it implies is that they have to live within these polytopes, but what are the constraints that you can derive? For example, can we prove the weak gravity conjecture? And of course, all of these, anytime you have beyond standard model physics, that means that when you're considering these higher dimension operators in terms of F4, you're going to have corrections to these coefficients. And also these corrections are also run with an RG. And all of these corrections, basically we're saying that if the theory is unitary, has a unitary completion in the UV, then all of these corrections has to lie within these second polytope that I've discussed. And so it's just going to be interesting to see what actually these constraints imply, or does it imply any constraints at all. So yeah, maybe I should increase this. Thank you very much.
Question?
Beside the Lorentz and conformal, can you read the other symmetry from this polygon? Like gauge symmetry or supersymmetry?
Well, I mean, of course, gauge symmetry is not a physical symmetry. So I mean, by definition, it's not a physical symmetry. So we're really only talking about global symmetry. Now, certainly, of course, we can talk about what constraints if you assume further symmetries. For example, if you assume that there's other global symmetries, then you can now try to construct. So these are the symmetry. These are the polynomials that are restricted from the fact that you only have Lorentz symmetry. So if you have further global symmetry, for example, you can ask, what if my UV completion is just random ordinary field theory? That would mean that the UV completion only involves spins that are up to massive spins that are up to 2, for example. And then you can construct the space which is only spanned by these vertices only with spins up to 2. And so depending on what kind of assumptions you have. And you can do the maximal assumption. For example, you assume that there's infinite symmetry, the Yangian symmetry. And then you'll go back to the polytope that I discussed in the beginning of my talk, which is this amplitude hedron for n equals 4 super Yang males. So yeah, you can gradually add more symmetry and try to see what kind of new constraints you have.
So if I understand you correctly, you draw a polytope for like dimension 6 operator, and then you draw another one for dimension 8 operator, so on. But I mean, if you were to have a UV completion, what happens is not just the correlation among dimension 6 operator, there's also going to be correlation among the coefficient between dimension 6, dimension 8, dimension 10 operator, and so on and so forth.
Right.
So how do you see that correlation?
Yeah, so that will be a more detailed analysis. So, for example, once you have, let's say you have a point here, then this should correspond, because this corresponds to a particular completion of the, so the statement is that, what I've talked about is that C squared is bigger than 0, right? These coefficients of C squared. So these dimension 6, dimension 8 operators are coming from particular C squared. So the constraint is that these same C squared is governing these expansion at dimension, so the same set of C squared is governing the dimension 6, dimension 8, dimension 10 operator. So that's an extra constraint you can start to try to impose. That the same set of C squared is controlling the fact that the dimension 6, dimension 8 operators are sitting at the particular point in your polytope. So that would be the constraint. It's the same set of C squared.
Right, exactly. So in this sense, even within field theory, you can ask, just given that the assumption you don't have a particle with spin up to spin 2,
right,
then you should be able to map out for each
exactly. Then you
UV completion what's the trajectory
right
for these.
Yeah, you can actually know what actually particular these C are, up to the overall rescaling, of course, because we're talking about things projectively, right? But the ratios between the different C's is going to be fixed by the fact that there's a particular point in this polytope.
You showed some graph with the streaming, but I missed the point. In what sense streaming is special?
In what
Show
sense?
some-
In what sense string is special? Well, I mean, it's just a visual sense that string is special. It's just that, yeah, if you look at the graph here, then the string theory answers are very close to the allowed space of your boundary. Of course, it has to lie within the 10-dimension space because it's really a 10-dimension completion. So, I mean, it's just a visual statement, but as you go to higher and higher polytope, you'll see that it's actually moving closer and closer to one of the vertices.
But when you say spinning amplitude, is the 2D amplitude or including loops and so on?
Oh, just street. Right. So one of the things I haven't said which I haven't stressed is that this there's also besides Lorentzian invariance and unitary, there's also another assumption, which is that your UV completion contains a perturbative parameter, so that you can have a separation between the loops and the tree. So we're talking about the perturbative completions.
Okay, I think we need time, so let's thank the speaker again.